Now, how to verify a message that we received hasn't been modified and it comes from the right sender, so authentication. And there are different approaches for authentication. And what we finished, so the receiver receives a message, they want to make sure that nothing has changed, and they want to make sure, or they want to make sure that the person who sent it is who they claim to be. There are different approaches for doing that. We saw last week towards the end of the lecture, we can use symmetric key encryption to provide authentication. Just by encrypting a message using symmetric key encryption, the concept is when we receive a message, if it successfully decrypts, that is, I have ciphertext, I decrypt with the key that I've shared with user A. If it successfully decrypts, that means it must have been encrypted with that key shared with user A, meaning it must have come from user A or from me. Okay, so if it doesn't successfully decrypt, I receive ciphertext and it doesn't decrypt using the key that I shared with A, then it means that message either did not come from A or has been modified along the way. Okay, so it provides authentication using symmetric key encryption. The problem with using symmetric key encryption is that although it works, it can be expensive in terms of computation in some cases. Sometimes we don't need to encrypt the entire message. Sometimes we just want to authenticate and not provide confidentiality. So there are other techniques which just provide authentication but don't provide confidentiality. And there are different approaches. Message authentication codes are one and hash functions another. We'll briefly mention MACs and a bit more time on hash functions, and then after we go through another encryption approach, public key encryption, we'll spend more time on hash functions and digital signatures, a key or an important part for authentication used in the internet, digital signatures. So we may go through quickly some of these slides if they're not absolutely necessary. Went through that last week. Message authentication codes, similar to symmetric key encryption. What we do is we have some algorithm, some function, F. We take our message, M. We take a shared secret key, K. And we apply some algorithm to get some code called a MAC, a message authentication code, as an output. Some usually short, maybe 128-bit value. And when we send the message, so the source does this, they take their message, calculate using a key the MAC for that message, and they send both the message and the MAC across the network. And then the receiver verifies the message by checking the MAC. What the receiver does is they take the received message and recalculate the MAC using the same shared secret key. And if it matches the received MAC, so the calculated MAC at the receiver matches the received MAC, then they verify that nothing has been modified. Shown in this diagram. Source has a message, M. Here the function is shown as C. So on the previous slide, the function F is shown as C. They take the message and a shared secret key and apply some function. And as the output, they get what we call a MAC, sometimes called a tag. Say a short, usually 128 bits or in the order of that, short code that should be unique for this message and key pair. And they send the original message and the MAC value across the network to the destination. So this is the concatenation operation. The 2 bars is short for concatenate. Take the message, not encrypted, just a plain text message, and combine it with the MAC and send both of them across the network. And this is what's received by the receiver, the message M, and this grey box represents the MAC of that message. The MAC of M using key K. When you receive this message, the receiver needs to verify, has the message been modified, and did it come from the right person? Maybe someone pretending to be user A sent this message. To verify, what they do is they take the received message, calculate using the same function, the MAC, using the same key, and they get a MAC as an output, and they compare to the received value of the MAC. If they are the same, everything is assumed to be okay. If they are different, it assumes something's gone wrong. Maybe someone sent a fake message, maybe someone's changed the message. So if they're different, then we ignore or we disregard the message, maybe try some other means to get the message. It works assuming that the MAC function is such that a malicious user cannot determine the MAC value without knowing the key. Okay? It's the same principle as symmetric key encryption here. If we get a MAC which matches this value using this key, then it means the value received must have been created with this key. And the only person who has this key is the original sender. A malicious user tries to pretend to be our user A. They don't have the key K to make the MAC. Okay. The same with symmetric encryption. If a malicious user tries to send a message to me, then they don't have the key of the original user they're trying to pretend to be. Let's go back. So the MAC, a MAC function, F here, C on the next slide, is some algorithm that takes some key and message and produces usually a short, unique, or practically unique value. That is, if we change the key, we'll get a different value. If we change the message, we'll get a different value. So that if someone tries to pretend to be a user, then to get the same MAC, they need to know the key and the message. So if the message is known, then they need to know the key, and if they don't know the key, they cannot generate the MAC value. This is one part we're not going to go into any more details. We'll see some more examples of authentication after we go through hash functions, very similar hash functions, and after we get to digital signatures. If we need this, we'll return and go through details later in another topic, but I think we won't need it for the other topics. At least know that a MAC can be used for authentication. That is, in practical situations, if we use a good message authentication code function, then I receive a message with a MAC, I can verify. Has it been modified? Did it come from the right source? The right source is the person who has the same shared secret key with me. If it is modified along the way, I'll be able to detect that. And if it comes from some malicious user pretending to be user A, user B will be able to detect that. We'll see some related examples after we go through hash functions, and that'll become a bit more clearer. As I said, we want to skip some parts here so we can get into the practical details later. There are different MAC functions, same as there are different encryption functions. There's AES, DES, and so on. In MACs, there are different MAC functions. Some of them are listed here: OMAC, PMAC, UMAC, and so on. One of the common ones used in practice today and in the internet is called HMAC. It turns out it's a MAC function that uses a hash function. So we need to explain hash functions for this to make sense, and that's in the next topic, or the next few slides. So in practice, to provide a MAC for authentication, often hash functions are used. So let's talk about hash functions. We won't look at the attacks. We'll just summarize that in most cases, for good MACs, the amount of effort it takes to brute force and break the MAC, to defeat it, if we use a key with k bits, and the output value here is n bits, the code or the tag is n bits in length, then attacks take approximately the minimum of 2 to the power of k and 2 to the power of n. That means if I have a 64-bit key and a 128-bit code, so k is 64, n is 128, the minimum would be 2 to the power of 64. Okay, so if k is 64, n is 128, then the amount of effort to break the MAC is equivalent to 2 to the power of 64. So think of brute force attacks on our ciphers. The amount of effort to brute force a cipher depends upon the key length. With a MAC, it depends upon the minimum of the key length and the tag length. If my tag is 20 bits, n is 20, my key is 64 bits, my MAC is just as strong as the tag, which is very weak. 2 to the power of 20 can be brute force quite easily. So we need to choose the code length or the tag length to be long enough and the key length to be long enough such that a brute force is not possible. Typically, the key lengths are the same as encryption algorithms, 64 bits, 128 bits, and the MACs, the code lengths, are also 128 bits. Let's look at hash functions, and some of the characteristics of MACs will start to make some more sense. What's a hash function? Everyone should know basics of hash functions. You should have covered them in some data structures or algorithms course in earlier years. Basically, some function that takes some variable length input, m, our message, for example, takes some variable length input and produce a fixed length, usually short output, called the hash value. So we have a message m, a 1 megabyte message. We apply our hash function on that message and we should get some short hash value, lowercase h in this slide, as an output. Short, let's say 64 bits, 128 bits hash value. And it should have some characteristics. And the practical ones are that if I apply the same hash function on 2 different messages, I'll get 2 different hash values as output. And the hash value should be random looking. So there should be no structure in the hash value. If I hash a message, I shouldn't, the output hash value shouldn't look like it depends upon the message content. So hash one message, I get one hash value. Hash a slightly different message, I should get a different hash value. Hash the same message again, I get the same hash value. Okay, it's a function here. A cryptographic hash function is one that's used for cryptographic techniques in security. And it has usually stricter requirements in terms of what the output of the hash function should be. And generally those requirements are denoted as the one-way property and the collision-free property. And similar to what we've just said, but there's some strict measurements of them. So if we have a message and we take the hash, we get a hash value. It should be hard, given the hash value, to find the original message. That's the one-way property. It should be easy to take a message, calculate the hash and get a hash value, but it should be hard to take that hash value and find the original message. So it should be easy to go one way, but hard to go back in the inverse direction. So some function such that this property holds, is usually required. Another way to state that, it should be hard, a cryptographic hash function, it should be hard to find some message that maps to some known hash value. So if I have a hash value as an attacker, it should be hard for me to find another message that produces that hash value, which is really, given a hash value, find a message. If we have that one-way property of our hash function, we can achieve different security objectives. Another property is collision-free. It should be hard to find two different messages, M1, M2, that produce the same hash value. Okay. So if our hash function has this property, we say it's collision-free. If it has the property that, given a hash value, I can't find a message, it has the one-way property. And they have different benefits in cryptography. We will use it often for authentication, hash values. Let's look at this example in a bit of detail to see how we can use it for authentication. Here, similar to the MAC, instead of using a MAC, we're using a hash function. We want to send a message from A to B, and we want to allow B to verify that the message hasn't been modified and that the message comes from A, not from some malicious user. So what A does, takes the message, applies a hash function on that message, assuming we have some chosen hash function, produces a short value as an output, the hash value here. Then we encrypt that hash value with a symmetric key cipher and with a shared key between A and B. No one else has K. It should be shared secret. A malicious user should not have K. Encrypt the hash value and send that encrypted hash value along with the message. Remember, this is concatenation. Take the message and the encrypted hash value and send them across the network. Received by B. Malicious user is here. They intercept the message. They intercept what was sent. Can the malicious user read the message contents? In this example, can a malicious user see M? Hands up for yes. Hands up for no. Try again. And I want to see all the hands over these two questions. In this case, the malicious user intercepts at this point. So this has been sent across the network. Malicious user intercepts here. They don't have the secret key. They don't know K. That's our assumption that the malicious user cannot know the secret. Only A and B know the secret. Can the malicious user see the message, the contents of the message? Hands up for yes. Hands up for no. Okay. The answer is yes, they can. Okay, let's try and draw that and make sure that's clear for everyone. A similar picture, but we'll use some extra notation. So we have our user A sending a message to B, the normal scenario. And we'd start with a message, and using our approach, we take a hash of the message and then encrypt that hash value. I'll not draw the boxes, but we take the message and we get a hash of the message encrypted with some key. That's the lower half. And here's the message, and we combine them. We have the concatenation. That's my approximation of our picture. What's sent across the network? M concatenated with the encrypted hash value. That's sent across the network in this example. So that's what you need to try and read from the diagram. The message concatenated with the encrypted hash value. Because what the source did was took the message, calculated the hash of that message, encrypted that hash value, then combined the result of that with the original message, then sends it all across the network. So that's this step. So sent across the network. Now, someone intercepts this component. They can see the message. It's here. It's not encrypted. So we say if we send this message across the network and someone intercepts, then of course someone can read the message. The only way we can prevent them from reading the contents is to encrypt that message. And we did not encrypt the message. So in fact, this example, we're not providing any secrecy of the message. It's not our aim. I don't care if someone reads the message. Not my problem. It's public. Anyone can read the message. But I want to make sure that no one changes the message, or that no one pretends to be me sending the message. That's our objective in this example. That is, we want to provide authentication. We don't want to provide confidentiality. In some applications, we have that requirement. We don't always need to keep our message secret. So the answer to our question was yes, the attacker can see the message contents. Okay. Now we'll come back to the attacker in a moment. So the objective is to make sure the attacker can't change the message without it being detected. And what the receiver does is when they receive the message plus the encrypted hash value, they take a hash of the message received. They decrypt the encrypted hash value received, that's here, using the same key as it was encrypted with, hopefully, and compare the values. If they match, everything's assumed to be okay. If not, assume something went wrong. Let's see what an attacker can do. Let's introduce some attacker into this scenario and see whether they can, for example, modify the message. So again, we have A, B, and we'll have some malicious user, Mao. A sends the message which was M, same as before, concatenated with the encrypted hash value. And instead of writing K, let's be more precise and let's say it's KAB. Hash of M. That's what's sent across the network. Where KAB means this key is shared and known by A and B. The malicious user will not know this key, because otherwise it's not secret. So KAB is the secret key shared between A and B. Sends that to B. Let's consider the case that malicious user intercepts before it gets to B. So it goes instead to the malicious user. And the malicious user's aim is to modify the message, send it to B, and hope that B thinks this modified message came from A. That's our aim as the attacker. What do we do? So we're going to send a modified message to B. What can we do as an attacker in this case? Okay, let's try some different things as the attacker. We've got this. Let's say the message is decrease the malicious user's salary by 10,000 baht. And this is encrypted of the hash value. Malicious user changes the message to increase instead of decrease. So just changes one part of the message. Let's denote the modified message as M prime, meaning it's a modified version of M. And then they concatenate that with what? They must concatenate with the encrypted some key and the hash of some of the message. What can they do as the attacker? They change the message. Well, they've got different approaches. What they could do is not modify this. Okay? That is, this is concatenated. Let's say the message is 1 megabyte, and this value is 128 bits. So all the attacker does is replaces the first 1 megabyte with their new message and takes the last 128 bits and adds it to the end. Let's try and see what happens if we do that. The attacker just changes the message but doesn't change the last part. So what would we have? What can we do? We can change, if we keep this as the same as before. We don't know the key. What we do as the attacker is just take whatever these bits are. I don't know what the key is, but I know that if we take the hash of the original message, encrypt with KAB, and it produces 128 bits, I just take those 128 bits and add them to the end of my new message. And I send that to B. When B receives this, they perform the verification steps. And back to our diagram here, the verification steps are B. Whatever we receive, take the hash of the received message and decrypt the last part with the key shared between A and B and compare. Let's try that. So B receives, let's find some space. They take a hash of the received message. What's received? M prime. And they decrypt, so they take a hash of this part and decrypt this part. When we decrypt this part, what do we get? So B received a message. They think it's from A. What key do they use to decrypt? What key do they use? KAB. So I've got this. I need to decrypt it. It was encrypted. I think the message is from B, therefore I decrypt. Sorry, I think the message is from A, therefore I decrypt with key AB. Okay. So decrypting this with key AB will produce the original plaintext. If we encrypt this value with key AB and then decrypt that with key AB, we'll get HM back as the output. So I've done the two steps. So what I'm trying to draw here is at the top is this step of take the hash of the received message and at the bottom decrypt using the key and compare the outputs. So the hash of the received message, the decrypted part of this, are they the same? No, assuming our hash function has the property that if we hash two different messages, we'll get two different hash values. That's what we said as a cryptographic hash function. We want the property such that we cannot get collisions. A collision is when we hash two messages and get the same hash value. If it has the property that such collisions are not possible, then what B does, they calculate hash of M prime, they calculate hash of M. They should be different values, because the hash of two different messages should be two different values. That's our property. Therefore, they compare them and they're different, and now B recognises something's gone wrong. They assume there's some attack. They don't know what's gone wrong, but they know something has gone wrong, and they don't trust the message. So this is how we've used hash functions in this case to provide authentication in the case that the malicious user tried to change the message. What happens if the malicious user changes the message? B detects that change. And we take advantage of the property of the hash functions to do that detection. What else can the attacker do? Send the key.
The modified key to be.
Okay, try a modified key.
Send from A.
Okay. Let's go back and see if we can modify the message from the attacker's point of view and try and fool B into thinking that they've received a message from A. So in this case, let's try from B's perspective, malicious user's perspective. We modify the message as before. We recalculate the hash value. So we take the hash of M prime. We've got the modified message. We calculate the hash of that, hash of M prime, and we encrypt with what key? What do we encrypt with? K. Can we encrypt with KAB? No, we cannot, because the malicious user doesn't know KAB. It should be secret between A and B. So we cannot encrypt with KAB. Let's say we encrypt with some other key. K. The key of the malicious user, whatever we want to call it. We cannot use KAB. We send that to B. What does B do? B does the verification. They take the hash of M prime, hash of the received message, and they get the hash of M prime, and they decrypt this part. They decrypt, I'll write it, they decrypt, and I'll not try and write it again, this. Okay. They decrypt all of that using what key? KAB. B receives a message, they think it's from A, therefore they'll try and decrypt using the key shared with A, KAB. What happens? Well, so this was encrypted with some malicious key, and then we decrypt it with a different key. What happens? We will not get this as an output. We'll get an error. Or we will not get the same plaintext. That's the property of our encryption, that if we encrypt plaintext with one key, and then decrypt the corresponding ciphertext with a different key, we will not get the original plaintext as an output. So we will not get H of M prime as an output here, and when we compare it to here, they'll be different. And therefore B has detected something's gone wrong. So in that case, our attack by the malicious user was detected. Any other way we can be malicious?
Repeat the message.
Sorry?
Repeat the message.
Repeat the message, send it again. So A sends this message to B, malicious user, and B receives the message. And then tomorrow, after the malicious user intercepted, he sends the same message to B. Yeah, that's possible. That's a replay attack. Remember, we listed some attacks. One of them was the replay attack, where you replay an old message. B still thinks the message is from A. The only way to stop such an attack is to include, maybe inside the message, some timestamp. Okay? So a replay attack is just resend the same message again. And using the hash doesn't prevent or doesn't allow us to detect such an attack. But we don't get to modify the message in a replay attack. And to detect replay attacks, if we include some timestamp, in practice we can often detect them. I know that this message I received yesterday, I've received it again today. Why? Wrong time. Maybe it's an attack. So yes, we could, but it doesn't allow the malicious user to modify the message. Can we modify the message some way? Well, I think if you explore the possibilities, you'll see if we want to modify the message, we'll either need to know the key KAB, and we assume we don't know that. Okay, so that's not a possible attack. Or we need to find a message, a modified message, that has the same hash function as the original message. That was our previous case when we did this attack. If the malicious user could find M prime, which has the same hash function as the hash of M, the hash value of M, if these two are the same, then our attack would be successful. So that leads to our property of hash functions. We need a hash function such that it's practically impossible for an attacker to find two messages with the same hash value. If we have a message increase or decrease Mal's salary by 10,000 baht and the hash value was H of M, and malicious user found another message which was different, and it turned out to be increase Mal's salary by 10,000 baht, and the hash value of this modified message was the same of the hash of the original message, then this attack would be successful. B would receive the message thinking it's from A, hasn't been modified, and would accept the message. So the property we require in this case is that a malicious user cannot find a message with the same hash value as the original message. We cannot find a collision in the hash space. If we have that property, then this is successful in preventing attacks or detecting attacks. Just going back. It should be, for a cryptographic hash function, it should be hard for an attacker to find two messages that produce the same hash value. If they can, then they can perform an attack that will go undetected. We'll see another example of hash functions when we look at digital signatures. So a similar diagram to what we just saw. This case we used a hash function combined with symmetric key encryption. So this E and D are symmetric key encryption. In fact, there are alternatives to doing this. This is just one example. There are others. What are some real hash functions or the algorithms. MD5 is a common one, has been around for a long time. Message Digest 5, developed by Ron Rivest. You'll see his name come up later. It created a 128-bit hash value. So you take any message, you apply MD5 algorithm, and you get a 128-bit hash value. The aim was that if you apply the algorithm on two different messages, you'll get two different hash values. But impossible for any hash function. Because if you take any length input and map it to a fixed small length output, then there are many more inputs that, in theory, many more inputs than there are possible outputs. Therefore, multiple inputs must map to the same output. But in practice, with a 128-bit hash value, gives us 2 to the power of 128 possible hash values. As long as the number of possible inputs in practice is less than that, then we can start to achieve no collisions in practice. So how many files are there in the world? Well, I don't know, but is there 2 to the power of 128 files in the world? Well, maybe not. So the chance of getting two messages that produce the same hash value must be very, very low. Okay? It's not impossible in theory, but it needs to be practically impossible. So in practice, it's very, very low. But with MD5, generated a 128-bit hash value, it was commonly used and still is commonly used in many applications. You download a file from the internet, sometimes the website will include the hash of the file. Allow you to, once you download the file, to check that the file you downloaded matches the file that was on the server, in case there were errors with the download, or maybe in case someone has intercepted and modified the file along the way. That was the idea. Turns out MD5 is subject to attacks. There are known attacks such that it's no longer recommended today for secure applications. Let's look at an example. Different software will calculate the MD5 hash value for an input. We've got several examples. I've got some plain text message. Okay, that's my file, that's the input. And I've got a program called MD5 sum. It calculates the MD5 hash of some input. And there's the hash value in hexadecimal. Okay, this, what is it? 32 hexadecimal digits, 128 bits. So that's the hash value of this text. If I take a different message, I should get a different hash value. Let's try a different message. Here's our different message. The first bit, it turns out, is changed. So I've changed one bit. So this text message we can represent as binary. If I just change one bit, it changes in ASCII the H to an F. Okay? We can check the binary and you'll see that just one bit has changed in the input. We take the hash of that second file. Is it going to be, what's it going to be? Anyone? Is it going to be similar to this, the same, or completely different? Completely different. Okay, that's our goal. Change with two different messages, we produce two different hash values, and effectively random hash values. There's no relationship between these two. Even though there's only one bit different in the input, many bits are different in the output. That's our goal of our hash function, and that's true in that case. And there are other hash functions we'll see. SHA, we'll see an example. But it turns out, although that case worked well, I got two different inputs, two different outputs. With MD5, there are known weaknesses that it becomes relatively easy to find two different inputs that produce the same output. And if we can do that, we can defeat the authentication mechanisms that we use it for. So MD5 is considered insecure from that perspective. I've got two different files. File 1 or file and file 2.txt. Same size, they're 128 bits. Okay, so they're not in fact ASCII, they're just binary files. So I will not show the contents. I would look at the binary form of those files. XXD is a program that shows the hexadecimal, the binary contents of a file. The first one is that, and the second one, are they the same, the files? This is not the hash, this is just the file contents. All right, this is the ASCII. This is hexadecimal. You see they're the same most of the way, but in fact there are some small, I think there are 5 or 6 bits which are different. Can we see on this point, where BDF2, BD72 in hexadecimal. There's a bit that's different here. So the files are slightly different. Okay, they're 128 bits in length, but several bits are different. They're almost the same but different. Okay, let's calculate the hash of each of them. The MD5 of the first file. And what should we get? Different file inputs. What's the hash value of the second file? It's the same. This is the weakness of MD5. It's possible to find two different inputs that produce the same hash value. And someone else found these. They'd done a lot of analysis to find these two values. They differ by several bits, but when you apply the MD5 hash on both of them, you'll get the same hash value. In that case, our authentication scheme will not work. Because what the attacker can do, if this was the original file, the attacker would modify the original file to be this one, this M prime, and send that on to B. B would do the verification. It would notice, the hash values match, therefore I'll accept this message. MD5 has this weakness in that you can find collisions between different inputs. That's why it's no longer recommended. So that's an exception in that case. SHA, the secure hash algorithm, was developed as an improvement and has gone over several variations. The original SHA, SHA-1, SHA-2, SHA-3 is being developed at the moment. SHA-2 is commonly recommended at the moment as being a secure hash function. SHA-1 and SHA-0 have some theoretical limitations and are not recommended in most cases. SHA-3 is being developed as the next version. They produce different output lengths. You can choose the output length. MD5 was 128 bits. The basic output length of SHA was 160 bits, but you can choose 224, 256, and up to 512 bits as output. The longer the output, the less chance of collisions. That's just some details about SHA. You've all set up your virtual network because there's a homework assignment that's going to use it this week, due next week. So here's the base file, 547 megabytes. We can do the SHA sum, I remember, SHA-1 sum, I think. Calculate using the SHA algorithm and the hash of that, the contents of the file, not the file name, the contents of the file it calculates. Okay? If you modify the file, you'll get a different hash value, and I'm not going to do that here. And there are other hash algorithms, but the main ones recommended today are SHA-2. Okay? But you'll see MD5 in use as well. We will not cover this. This is a little bit more theory about those properties of one-way property and the ability to have no collisions, collision-free. This is some of the theory of it. It turns out, in terms of brute force attacks, preventing collisions is the hardest thing to do. And it's equivalent to if we have a hash length of n bits, so MD5 was 128 bits, to provide the one-way property, for example, a brute force attack to defeat that property requires 2 to the power of n operations. With MD5, 2 to the power of 128 operations. To do a hash of 2 to the power of 128 times would take forever. But to defeat the collision property required by some applications, it takes 2 to the power of n divided by 2 operations. So with MD5 being 128 bits, 2 to the power of 64 operations. From the attacker's perspective, finding collisions, defeating the collision-free property, is easier, much, much easier, than finding or defeating the one-way property. So when we want to prevent collisions, we need to consider that the hash length, or half of the hash length, indicates how much effort a brute force attack takes. But we will not cover any of this theory. Nor this. Later we'll see during this course some different examples of where we use hash functions, like in digital signatures, virus detection, passwords. So hash functions are used in different applications. We'll see passwords, viruses, and digital signatures in this course. How fast to do an MD5 collision attack today? That's a good task for you to find. I will not give a demo here. But you can basically today, you can buy hardware. Many people buy GPUs, graphics processors, and can defeat MD5 quite quickly, okay, for a very low cost. MD5 is considered broken. You can do billions of hashes per second quite easily with standard hardware. So, to authenticate, to check that the message we received has not been modified or comes from the right person, we've got different approaches. Symmetric key encryption, we briefly mentioned message authentication codes, but not many details. Hash functions are quite important for that. We'll see that there's something called digital signatures, which combines hash functions with public key encryption. So first, let's talk about what is public key encryption. It's not just for authentication. It's generally for encrypting. Remember Caesar? So from the beginning of when ciphers were known, up until the last 40 or 50 years, all of the encryption algorithms were using symmetric key cryptography. DES, AES are all symmetric key encryption. That is, source and destination use the same shared secret key. Okay? Both of them must have the same key. In the 60s, 70s, and around that time, different organisations and people started to design or develop a new technology for encryption called public key cryptography today, or asymmetric key cryptography. It was first publicly reported by Diffie and Hellman in 1976, so they wrote some paper about public key cryptography. And one of the first and still one of the most popular algorithms that implement it is RSA by three guys called Revest, Shamir and Edelman. Revest developed MD5 and many other ciphers. And it turned out later that people found out that even though they were the first to publicly introduce this, there are security organisations that secretly developed similar techniques in the past. So now really we say there's symmetric key cryptography and public key cryptography, two different approaches. In symmetric key cryptography, we use the same secret key for both encryption and decryption. In public key cryptography, or also called asymmetric, we use one key for encryption and a different but related key for decryption. Okay, so we have asymmetry between the keys. We don't have the same key at both sides, we have two different keys. But the keys are related somehow. What we need in most cases for public key cryptography is that we'll see that one of the keys, so we have two different keys, one of them will be made public. Everyone knows it. The other one will be private. It's kept secret. Therefore, we'll see for it to work, it must be hard to find the private key if you know the public key. Actually, we'll see this come up in the later slide, I think. Let's get into the details. So we have two keys now, two different keys, not one shared secret key. A public key and a private key. They're used in different ways, depending on what we want to achieve. If we want to have secret messages, that is confidentiality, I have a message, I want to send it to you, and I don't want anyone else to be able to read the message except you. That's my aim. Then how we use public key cryptography is that, so for secrecy, I encrypt the message using I encrypt the message using a public key, and it will turn out to be your public key. I encrypt with a public key, send to the other person, and they decrypt with their private key. Okay? For secrecy, we encrypt with a public key, decrypt with a private key. For authentication, the case where I want to send a message to someone, I don't care if someone else reads the contents, but I want to make sure that the receiver can verify that it came from me, not from someone pretending to be me. So authentication, then we use the keys in the opposite order. I will encrypt with my private key, send to you, and you will decrypt with my public key. So we'll see this in a number of examples. The main point so far is that we have two keys. So we think we have a key pair, a public and a private key. The private key, as the name suggests, must be kept secret. No one else knows it. Only one person in the world knows that private key. But the corresponding public key, everyone can know it. It doesn't matter who knows it. So we talk that each user now has a pair of keys. So user A will often denote as having a pair of keys, their public key, the public key of user A, and the private key of user A. So we use PU to mean public key, PR to mean private key. So I think each user has their own pair of keys. Given that, let's see how we provide confidentiality. So this is the aim of user A on the left, wants to send a message to user B on the right, and the message should be kept confidential such that no one else can read the contents of M, the message. That's the aim. If someone intercepts the ciphertext, they shouldn't be able to find the original message. How do we do that? We take our message, our plain text M, we use a public key encryption algorithm, and we encrypt the message using the public key of the destination. So remember, this is B, this is A. A encrypts our message using the public key of B. Get some ciphertext as output, where the ciphertext is the encryption of the message using the public key of B. Sends that across the network. B receives this ciphertext. So now they want to read the message. They decrypt using their private key. And the algorithm must be designed and the keys must be chosen such that if we can decrypt with the private key of B, we will get the original message as the output. So we need an algorithm where that property will hold. That is, if a message is encrypted with the public key and then the ciphertext is decrypted with the corresponding private key, we should get the original plaintext as the output. If not, then this system won't work. Assuming that works, encrypt with one key, can only decrypt with the other key, what can an attacker do to read the message? The attacker intercepts the ciphertext. They want to find M. What do? Well, if they have the ciphertext, to decrypt the ciphertext, they need to use a key. Which key? They need to use the private key of B. And by definition, the private key of B will not be known by the attacker because it must be private to B only. So, assuming our algorithms are designed correctly and our keys are chosen correctly, the attacker can intercept the ciphertext but will not be able to get the message M. And we've achieved our aim of confidentiality. So to keep a message secret, encrypt with the destination's public key, and the destination will decrypt with their private key. Okay, so always remember that ordering of keys for confidentiality. And the algorithm must be such that only the person with the private key can successfully decrypt. If I receive this ciphertext and try to decrypt it using some other private key, my private key, for example, then I'll get an error. Or at least I will not get the original plaintext. I'll get some other random text. Similar, if in symmetric key cryptography, if I intercept a message and decrypt it with the wrong key, I will not get the plaintext as an output. That's the property of the algorithm. If you decrypt with the wrong key, you will not get the plaintext. The other common way where public key crypto is used is in authentication. I don't care who reads the message in this case, but user B, when they receive a message, want to be sure that it came from A, not someone pretending to be A. So what do? User A takes the message and they encrypt using the private key of A. Okay, I'm user A, I encrypt with my private key. I send the ciphertext to B across the network. B decrypts with the corresponding public key. If it was encrypted with the private key of A, B thinks, here's a message, it came from A, I will decrypt with the public key of A. And if we're using a secure public key algorithm, it should be such that if we encrypt with one key, it will only successfully decrypt with the other key in the key pair. So if I encrypt with the private key of A, I can only decrypt with the public key of A. If I try to decrypt with some other key, it will not work. We'll get an error. So how does this provide authentication? Let's say a malicious user wants to pretend to be A. Some malicious user is here. They send a fake message saying this is from A. They send it to B. They encrypt that message with the private key of who? Well, they cannot encrypt with the private key of A because they don't know it. So maybe they encrypt with the private key of the malicious user, send it to B. If B thinks it's from A, they'll decrypt with the public key of A, and they'll get an error. Let's look at those two examples. Or let's look at that attack first, just to make this clear. So let's say we have our two users. A sending a message to B, but we have a malicious user who's going to perform an attack and pretend to be A. So they're in fact going to send a message to B. It doesn't come from A. It comes from our malicious user, but they're pretending to be A. So what do? They have their message, and we encrypt that message with some key. We want to provide authentication in this example, the same as this case. Malicious user wants to send a message to B, pretend to be A, and wants to B to think it came from A and will trust the message. So we must encrypt the message with some key. What key can we encrypt with? Well, for authentication, we should encrypt with a private key. Actually, whose private key can the malicious user encrypt with? Well, they cannot encrypt with A's private key. They cannot encrypt with B's private key because they don't know them. They are private. Let's say they encrypt with the malicious user's private key, his own private key. He sends this message to B, but the from address in the message is user A. B receives a message, from user A, let's verify the message. So what B does is that they decrypt that. What do we have? What's received is this is the received message. Okay, this is what was sent. It's exactly the same as received. Okay. B receives it, thinks it's from A, so they decrypt it using the public key of A. It will be unsuccessful. That is, an error will be returned, or at least we'll be able to recognize that it didn't decrypt correctly, because we'll see the property we require of our algorithms, same with symmetric key, except we have two different keys. If we encrypt a message with the private key, it will only successfully decrypt if we use the corresponding public key. By the corresponding public key, I mean the key in the same pair. That is, this was encrypted with the malicious user's private key. It will only successfully decrypt using the malicious user's public key. It will not successfully decrypt using the public key of A. So when B tries to use the public key of A, they'll get some error from this decryption, which tells them something went wrong. It didn't come from A. So they'll detect that and realize, okay, don't trust this message. Any questions on the concepts of public key cryptography so far? We haven't spoke about the actual algorithms yet. We'll see some later, but the assumptions we're making is that every user has a key pair. Every user has their own public and private key. And the assumptions about the algorithm are that if we encrypt with one key in the pair, we can only successfully decrypt with the other key in the same pair. If I encrypt with Steve's private key, I can only successfully decrypt with Steve's public key. If I try a different key to decrypt, I'll get an error. That's the assumption. And in fact, in most cases, the ordering of the keys doesn't matter. If I encrypt with Steve's public key, you can only successfully decrypt with Steve's private key. If I encrypt with Steve's private key, I can only successfully decrypt with his public key. So as long as we use the corresponding key in the key pair, we'll successfully decrypt. And we use that for both confidentiality, encrypt with the public key of the destination, decrypt with the destination's private key. We can only decrypt the message if we have the private key of B, and only B has the private key of B, and therefore only B can decrypt the message. No one else in the world can decrypt this ciphertext. And for authentication, to verify where did the message come from, A encrypts with A's private key, B verifies by decrypting with the public key of A. Anyone can verify. Everyone has the public key of A. It's public. Everyone knows that value. So anyone can decrypt this ciphertext. It doesn't provide confidentiality. But all it provides is to be able to check this message must have come from A. If it decrypts with the public key of A, then it must have mean it was encrypted with the private key of A, which must have mean user A encrypted it. Therefore, it's proof that this message came from A. Okay. This is an important concept in a digital signature. We sign a message using your own private key. We'll see some details of the algorithms and being used in the next lecture. Let's just summarize. It turns out that public key cryptography, the algorithms available today for encrypting large amounts of data are very slow. Compared to symmetric key cryptography, they're very slow and therefore not very convenient to use. Turns out they're mostly used for authentication, to prove that this message came from a particular person. Digital signature is the concept. And there are some other applications of public key cryptography, like key exchange, which we may see in another topic. There are different algorithms available. RSA is a very popular one, but there are others. There's the concept of elliptic curve cryptography, which uses some different mathematics. Diffie-Hellman is an algorithm for exchanging keys. There's a digital signature standard for signing documents. We'll see them come up later. And I think this summarizes our requirements of our algorithms. So for general public key cryptography, first, we need it to be able to easily generate a pair of keys. Okay? Every user will need their own key pair. So we need it such that we can generate them quite easily. Your homework task will be to generate your own key pair. Okay? You use some software, it takes 1 second to generate. Okay? So that's easy. Given a key pair, it should be easy for one user, A in this case, to be able to encrypt using a public key some message. Okay? Encryption should be easy. That is fast. That's a practical requirement, not a security requirement. Similar, if some message is encrypted with the public key of B, then B who has the private key of B should be able to decrypt, so take the original ciphertext, decrypt with the private key, we should get the original message or plaintext back. That's a requirement. And it's a fundamental requirement, that is, encrypt plaintext to get ciphertext, decrypt the ciphertext must give us the original plaintext. That's the normal requirement of encryption. But now from an attacker's perspective, or the security of the algorithm, an attacker may know the public key. It's public, anyone can know it. If they know the public key and they know the ciphertext, again the ciphertext is sent across a network, and they know the algorithm, it should be practically impossible for the attacker to find the corresponding private key. Okay? Because if they can, it's no longer private. So given a public key, given the ciphertext, it should be impossible to find the private key. And note that the public key and private key are related somehow. They're not just random, they have some mathematical relationship. So if you know the public key, it should be hard to find the private key for the attacker. If the attacker similarly knows the public key, they know the ciphertext, they should be hard to find the original plaintext. So they shouldn't be able to decrypt unless they have the correct key. We require that. Here it says computationally infeasible, practically impossible. In theory it may be possible, but in practice it must be so slow that it would take millions of years to do so. This optional one, not so relevant at this point in time. So we've introduced a new concept for cryptography which uses two different keys now. And it's very important in many systems today, in the internet. And it turns out both symmetric key cryptography and public key cryptography are used in practice today, but often for different purposes. They have different advantages and disadvantages. We'll see some of them over this course. What we'll do on Thursday is look at a little bit about attacks, give an example of a public key cryptography algorithm and the security of it. And I think we'll skip key management and try and finish this topic on digital signatures, which will combine public key encryption and hash functions. And we'll see how they're combined to provide some form of signature. And let's hope and try and finish that on Thursday. Okay. Everyone's done the homework.